All right, so now we're going to look at this higher order asymptotic theory of estimation. So you might ask, well, what do I exactly mean by that, right? So we're going to look at, in particular, the covariance, the error covariance matrix, right? So you consider the sort of covariance matrix of an efficient estimator. And if you recall, what that means, it's like for the estimator to be efficient, is that this achieves the Kramer-Rao bound, which is G inverse over N, right, asymptotically. Which is to say that we ignore these high order terms, right? Which is of order 1 over n squared. Okay, so what we're hoping to achieve then, it's like in higher order asymptotic theory, as you might expect, is to take the analysis one order up, and in particular looking at this 1 over n squared term, and seeing how that behaves. Okay, so the higher order asymptotic theory right, evaluates this higher order term. And in particular, it's like, what you might ask is what that higher order term, what the coefficient in front of the higher order term is, right? And under what conditions that coefficient vanishes, right? So this makes it possible to sort of basically establish higher order convergence of estimators in the limit where n goes to infinity, right? So this is directly analogous to what happens, for example, if you're doing numerical ODE methods. It's like where you have a time step going to 0, right? And you say that the error scales like h or h squared or h cubed, right? So the higher the order it is, it's like in this small parameter, right? The faster the convergence is in some appropriate sense. So the small parameter here is 1 over n, and so you're looking at something which is the square of 1 over n, right? So that's the second order rate of convergence, if you will, if if that term it's like vanishes as well. So all right, so how do you go about doing this? Okay, so in order to compare the higher order errors, right, we're going to introduce sort of an asymptotic bias correction of the estimator. Okay, so this B, right, is So this comes from sort of this estimate we had before. Where if you recall, that's the expectation of the error in the W coordinate system, right? Okay, so well, yeah, all right. So, okay, so if we modify the estimator by u hat star is u hat minus the bias associated with u hat, okay, then the claim, as you might expect, that's the leading order bias. It's like, you know, if you actually, no, this is not what we want to do, right? So, yes, so the bias is just defined to be the expectation of the estimator minus the true value, right? So if you basically take this out, it's like then the first order sort of expectation, it's like disappears, okay? I mean, the expression which we had, it's like pertains to actually the estimation problem, so it will show up later intuitively. But anyway, so that's just the definition of the bias for now, right? So I'm going to correct for the bias. So then what happens is that the expectation of u hat star, right, minus u, right, is now not going to be first order, but second order, right? 1 over n squared. So I guess it's like here we're just talking about what happens if we're talking about the asymptotic case, right? And usually what happens is that, you know, it's like whenever you're looking at things asymptotically, it's like you just look at the leading order error term. And so what's basically happening is that if you remove, it's like the bias, which is the leading error term, if you will, it's like in the estimator, then what you would expect is that the expectation, it's like of the shifted estimator is going to be higher order, right? So that's basically what's happening. Okay, so this is called a bias corrected estimator. So if you want to compare, it's like these covariances of the various efficient estimators, we're going to use this bias corrected estimator. Okay. So, right, so I'm just going to state the theorem. It's like the actual calculations are nasty. And as you see in the book, it's like the actual calculations are done in a paper by Amari, okay, from 1985. So let me just sort of state the theorem. So the covariance matrix of a bias corrected efficient estimator is given by the following. So E so this is going to be GAB plus 1 over 2n gamma M 2S AB plus 2 HE2 S AB plus HM2 AAB plus something which is higher order. Okay. So all these terms, it's like which need to be explained. So where HE2 SAB is HEK EC HE FD lambda G CD G kappa lambda GAE GFB. All right, so that's a mouthful, okay, but the main point is that which is the square of the E embedding curvature of S and this H M2 AB, which is given by this expression is the square of the M embedding curvature of S. All right, so there's a curvature term which has to do with how S is embedded, and the curvature of that embedding is with respect to it's like the E connection, right? And then there is also, it's like a curvature, it's like of the embedding of S with respect to the M connection. Okay, so these are the two terms. And then there's one additional term which has to do with sort of the properties of the fiber, it's like of this ancillary family, right? And then this gamma M2S AB, which is gamma M A C D gamma M B E F G C E G D F. Right, is the square of the M connection of the coordinate system U in S. All right, so all right. So let me sort of make a few remarks about this, right? So So this E term, right, has to do with the extent to which the statistical model space S deviates from being a exponential family. Okay, so so this term sort of measures sort of deviation of S from an exponential family. So, so Efron refers to this as a statistical curvature. Okay. Sorry, this is the embedding curvature of A, right? Okay. So all this makes sense if you recall. It's like this generalized Pythagorean theorem, right? You always have the situation where one of the spaces is flat with respect to one of the affine connections, and the other sort of space is flat with respect to the other affine connection, right? So in this problem, it's like you have this S and you have this A of U. So you measure the curvature of S. It's like using this E connection in some sense, and you measure the curvature of this complementary space AU. It's like using this M curvature. Okay. Right. So as you might expect, you want this to be 0, you want this to be 0, and then this is something which you don't have as much of a choice in. Right. So this depends on the parametrization U in S. Okay. So the more it's like the connection is flat, it's like, you know, in this coordinates, it's like which we've defined, it's like on S, it's like the better it would be. Okay. So it should be remarked that this term here vanishes for a maximum likelihood estimator. Okay, so this vanishes for maximum likelihood estimator, and that's because you know, in that case F is M projection, right? So if F is M projection, then it's M, the fiber itself, you know, is going to give you something which is orthogonal, it's like to the surface, the submanifold S. Okay. Right. Okay. So anyhow, so this, you know, it's like it's a rather involved result. It's like, but more or less, it says that, you know, this sort of estimator is somehow as efficient as possible, right? If these curvature terms vanish, if you will. Okay, so let me just state that as a theorem. Right, the bias correcting efficient estimator is second order efficient when the embedding curvature embedding, shall we say, M curvature of AU vanishes at S, and the bias correction, so the bias corrected maximum likelihood estimator is second order efficient. Okay. All right, so why do we say that? We say that because if you look at all these terms, in some sense, you know, what happens, how S is embedded, and how what its E embedding curvature is something which you don't have a choice in, right? It's like you're given, it's like this statistical family S, that's something that you have. And you're also given the coordinatization, it's like of S, that's also given to you. So the only choice you have when you construct the estimator, given those parameters, is essentially the choice of projection, okay? And so the only part which you have direct control over when constructing the estimator is this curvature term, which involves the M embedding curvature, it's like of A of U, right? Which corresponds to this choice of projection in some sense, okay? So that's the part which you have direct control over. And as the remark says, this vanishes. It's like when you have the maximum likelihood estimator, because that is just M projection onto, it's like the submanifold S. Okay, so that's really sort of the content of the theorem, that when you do this bias correcting sort of efficient estimator, it is second order efficient. It's as good as you can get, you know, given the constraints which are sort of prescribed to you, which is again the choice of S and the choice of coordinatization of S. If this M curvature, it's like vanishes, it's like at S, right? Which is to say that this term, this term here vanishes. Okay. And in that situation, it's like and in particular, it's like, as we said, the bias corrected maximum likelihood estimator, which is M projection, has this term vanish, and so it is second order efficient, all right? And you can ask whether or not this is true of even higher order cases, but it turns out that sort of maximum likelihood estimator is not third order efficient, okay? And that was proved, it's like by Kano back in the late 90s, okay? So anyway, so that's basically what comes into play, but but nevertheless, it's like even though you don't have control over these two terms, it does still tell you something about how, it's like what kind of rates of approximation you have if you were given the ability to choose, it's like this, it's like model family, it's like of statistical models S, right? So depending again on what the E embedding curvature, it's like if S is in this family of it's like exponential families, right? The rates can differ. Okay. So anyway, let me just stop here for now.